Okay, so now we're going to start with chapter 11, which deals with the modern atomic theory and how it relates to the periodic table. Okay, so first of all, we're going to get into a brief history about how we arrive at our current understanding of the structure of the atom. The Greeks were the first to suggest that you can actually have the smallest fundamental unit of a substance of matter known as atoms. And based on this, early chemists performed several different experiments to delve into the nature of the atom, and their experiments lead to the Dalton's atomic theory, which I won't get into now because I think we covered it before. There are a couple of limitations of the Dalton's model, and this led to discoveries made by Thomson and Rutherford, which basically fine tuned some of our understanding of the atom. And while these models work reasonably well, there are some limitations yet still, which lead to more modern theories about the nature of the atom. So these are the theories we're going to look into in this chapter. So in order for us to get into these theories, we have to understand firstly the nature of electromagnetic radiation. So energy can travel through space in this form. For example, the energy that comes from the sun is largely because of the energy in the form of electromagnetic radiation. And this radiation exists as a waveform. So these are the different examples of EM radiation. As I mentioned before, light from the sun, but you have some other examples as well: X-rays, microwaves, radio waves, TV waves, and radiant heat. And as I was saying before, these forms of radiation, they show wave-like behavior, right? So basically, we all know what a wave looks like. We're going to see an example of what it looks like shortly. But before we get to that, one thing you need to understand is that all forms of electromagnetic radiation travels at the same speed in a vacuum. And the speed of travel is shown right here, 3.00 times 10 to the 8 meters per second. So the characteristics of the wave, firstly, you have a wavelength, right? So this is a waveform. The wavelength is basically the distance between two successive peaks, as you can see here, or two successive troughs, as you can see here. And the symbol that is used for wavelength is the Greek letter lambda, as you can see here. All right. So that's one characteristic of any waveform, and that is true of the electromagnetic radiation. It exists as a waveform and has a characteristic of wavelength. Waveforms also have frequency. Now, the frequency by definition is a number of wavelengths that passes a particular point per second. So if you see a waveform moving and you focus on one point and you see how many waves passes that particular point per second, then that's a frequency. And the unit of frequency is either second to the minus 1. In fact, let me write it down here. So the unit of frequency is second to the minus 1, which is the same thing as the hertz unit. So if you see second to the minus 1, or if you see hertz, it's the same thing as second to the minus 1. All right? So that's another property of wave that you need to know about. And then we have the speed. Now the speed basically is the product of the wavelength times the frequency. All right? So if the wavelength is in meters and the frequency is in seconds to the minus 1, then the unit of speed would be ms to the minus 1, or meters per second. All right? So the speed, of course, is how fast the wave moves through space. So we talk about the fact that radiation, light included, can exhibit wave-like behavior. But it turns out, and this might seem a bit confusing and counterintuitive, but it turns out that all forms of radiation display the properties of a stream of fast-moving particles. And these particles are called photons. Now, both the wave model and the particle model are used to explain the different properties of radiation, including light. So let us look at the full electromagnetic spectrum. This lists all the different forms of radiation, and in this particular diagram, they are ordered in terms of increasing wavelength going from left to right. So the lowest wavelength form of radiation would be gamma rays, followed by X-rays, followed by ultraviolet rays, and then within this narrow band here, going from 4 times 10 to the minus 7 to 7 times 10 to the minus 7 meters, you have what is known as a visible part of the electromagnetic radiation. So this represents all the different forms of radiation that our eyes are sensitive to. So at one end, you have violet, indigo, green, well, you have violet, indigo, blue, then you have green, and then you have yellow, then you have orange, and then you have red, right? So that's basically the electromagnetic spectrum. So as you can see, that type or that part of the radiation spectrum, EM spectrum, that our eyes are sensitive to is a very small part, all right? Then you have infrared, then you have microwave, and then you have radio wave to the extreme right, and those have the highest wavelength. And based on the fact that, let me bring up the pen function again, based on the fact that for the electromagnetic radiation spectrum, that c, which is constant, the speed of light, is equal to lambda times nu, based on the fact that there's an inverse relationship between wavelength and frequency, because when they multiply, it equals to a constant c. That means that as the wavelength increases, the frequency decreases. So in this particular case, the wavelength increases this way, right? So lambda increases this way, obviously, as we can see from this diagram, which means that going the other direction, let me do it. So here, the frequency nu increases, all right? So that's the relationship between frequency and wavelength for the electromagnetic radiation. So those forms of radiation, for example, gamma rays, have a wavelength of about 10 to the minus 12. So the wavelength is relatively small, so therefore you'd expect that the frequency of these forms of radiation will be very high. And for the radio waves, where the wavelength is very large, you'd expect that the frequency to be very small at that end. Okay, so let's talk about the Bohr atom, and let's see how we can tie in what we just discussed in relation to the Bohr model of the atom. So if you take white light, all right, and you pass it through a prism or diffraction grating, then you get a situation like this. So here we have the light source. The light is passed through a slit, so the beam emerging from the slit is allowed to hit a prism. Now the effect that the prism will have on the beam of light is that it splits the light up into different colors based on their different wavelengths or frequencies. So the light passes through the prism, and then when it emerges from the prism, it is projected onto a screen, and what you see are the different colors light, the different parts or different colors light of light, which corresponds to the visible part of the electromagnetic spectrum. So we call this a continuous spectrum. It is continuous because if you look at this spectrum going from one end to the next, there are no clear lines of demarcation between the different colors, right? You see that one color simply run into another. So the red basically runs into the orange, which runs into the yellow, which runs into the green, and so on and so forth. All right, so that's basically what the continuous spectrum looks like, and that is what is formed from white light. All right, so let me talk about the line spectrum. Now, the line spectrum you can get from a situation where if you have a gas that is trapped in a tube and you subject it to a discharge due to high temperatures or voltages, right, it produces light of different colors. And then when you allow the light to pass through the prism, just as we saw in the previous experimental setup, you're going to get what is known as a line spectrum. So the line spectrum looks something like this. I don't know if you can see it clearly here, but the next page will show you exactly what it looks like. Now, what we have here is what is known as a hydrogen lamp. It consists of hydrogen at very low pressure trapped in a tube, and it is subject to a potential difference or voltage. In other words, you have two electrodes stuck into both ends of the tube, and those electrodes are connected to an electricity source. So it produces light of a pink color, and that light is allowed to pass through the prism and splits up and is projected onto the screen, and you end up with your line spectrum. So as you can see, the line spectrum consists of several lines of different colors, and the different colors, of course, correspond to different wavelengths. All right, so that's very different from what we saw before, where we saw the continuous spectrum. So basically, you have specific lines, and you have dark regions within or between the lines. All right, so that's basically what the line spectrum looks like. So a more clearer picture of the line spectrum is seen here. So this is the line spectrum of hydrogen. All right, each line corresponds to the wavelength of energy emitted when you have an electron in the hydrogen atom falling from a higher energy level to a lower energy level. All right, so basically what happens to form the spectrum is that when the hydrogen is subjected to the potential difference or the voltage, the electrons in the atom gain energy, electrical energy, which allows it to be promoted from one lower energy level to a higher energy level. And in that unstable state, it will immediately relax back to the original state where the electron falls back to the lower energy level. And when the electron falls back to the lower energy level, it produces radiation, resulting in the line spectrum that we observe here. All right? Okay, so, and another thing I want to mention here is that this is not only true for hydrogen, but it's true for every element. Each element has its own unique set of emission lines, right? So if you did the same experiment with, let's say, sodium, or with helium, or with iron, then you'll see different line spectra, right? And each element has its own unique, basically atomic fingerprint, so to speak. That's what the line spectra basically represent. And this is basically how, for example, different elements in the sun are identified. What the scientists do, usually physicists, is that they look at the light emitted by the sun, and they somehow have their instruments designed so that they can identify the different line spectra for the different elements and compare it to what is known for their for the specific element, and by so doing you can identify particular elements present in the sun. Okay, so let's talk about Niels Bohr. He's the person who came up with a model to explain the observations that we saw. So he carried out research on the hydrogen atom, and he came up with a model of the hydrogen atom. And basically what you see here is a model, right? You have the nucleus here, and then according to Bohr, the electrons will travel in well-defined elliptical orbits surrounding the nucleus, all right? So in the hydrogen atom, that would be one electron. So the one electron can be in this orbital here, or this orbit, I should say, or in this orbit, or in that orbit, right? And these orbits are designated. So the first orbit here is called the n=1 orbit, and this is the n=2 orbit, and so on and so forth as you go away from the atom. So basically this is how the Bohr model explains what we just saw in terms of the line spectrum. It says that when an electron falls from a higher energy level to a lower energy level, a quantum of energy in the form of light is emitted from the atom. The color of the light emitted corresponds to one of the lines in the hydrogen spectrum. So therefore, when you have, for example, an electron falling from the third orbit, okay, it's not moving, I don't know what's going on here. Okay, I'm sorry about this, I don't know what's going on. Let me back up a bit here. Okay, so if you have an electron falling from the third orbit to the second orbit, that energy difference is equal to light emitted of a particular color. And in this case, it's the red color light, which gives the red line in the line spectrum of hydrogen. All right? So that explains the appearance of the red line. Now, if you have the electron falling from the third orbit to the first orbit, then that produces light of another color, green. And that is responsible for the green line that is observed in the line spectrum of hydrogen. And so on and so forth for the other lines. All right, so calculations were done to explain the existence of the other colored lines. And as you see in the previous examples, basically those colored lines are the result of the electron falling from higher energy orbits to lower energy orbits. All right. So the light is not, of course, emitted continuously. That's why you end up with a line spectrum instead of a continuous spectrum. And it says here that it is emitted in discrete packets known as quanta, right? So the particles of light that is emitted are known as quanta, all right? So there's a quanta of red light that is formed when the electron falls from the third orbit to the second orbit, all right? Of course, an electron can have one of several possible energies depending on the orbit it is located. So, as I said before, the orbit that is third from the nucleus is called the n equal 3 orbit. That's called the n equal 2 orbit, and this one is called the n equal 1. And of course, they can go higher up to infinity. All right. Now, Bohr's calculations succeeded very well in correlating what is observed experimentally with the energy levels for the hydrogen atom. But there's one problem, and the problem is that for heavier atoms, this model does not work well. And the main reason why it didn't work well is because for other atoms, you have more than one electron. Electrons repel each other, and that kind of distorts the energy levels as predicted by the Bohr model. So therefore, more work needed to be done in order to refine the theory put forward by Bohr so that we can explain the atomic structure or the line spectra for other atoms, which can lead to a greater understanding of the atomic structure. This guy, Louis de Broglie, and let me just apologize for possibly mispronouncing his name because his name is French, and I'm not a French speaker, so I'm quite sure that I'm massacring the name. But in any case, this guy, he considered the possibility that, okay, if EM radiation display both wave and particle behavior, then it is possible that particles that are moving display wave-like behavior as well, right? And he showed using an equation, which at this stage I don't think you need to know. I don't think I need to show you the equation, but basically he derived an equation which basically is used to calculate the wavelength associated with moving particles. And what he showed is that such wavelength for ordinary sized objects, meaning objects that we can see, right? Those wavelengths are too small to be observed. But when it comes to very small microscopic objects such as electrons, protons, etc., even an atom, then the wavelengths can be detected because they're large enough, all right? And then another guy by the name of Erwin Schrödinger, he came up with an equation. Now, thankfully, at this stage, you don't need to know what that equation is. However, that equation was a very important turning point in our understanding of particle behavior because Schrödinger's work led to basically a new branch of physics known as wave or quantum mechanics. And using this approach, it is shown that you can actually determine the probability of finding an electron within a certain region around the atom, all right? And therefore, what you'll find is that from this point on, we move away from this idea that electrons can be discovered or located within certain elliptical orbits as predicted by the Bohr model. Instead, we basically talk about a region in space where the probability of finding an electron is very high. And this is largely as a result of the work of Schrödinger. As you can see here in this line, one of the conclusions of the Schrödinger approach is that the actual location of an electron within an atom cannot be determined, all right? So this is one of the shortcomings of the Bohr model because the Bohr model seems to suggest that we can tell where an electron is within an orbit at a particular time. According to Schrödinger, that is not true, all right? Instead, we talk about the probability of finding an electron within a certain region around the atom, all right? So based on wave mechanics, which is, of course, the Schrödinger approach, it is clear that electrons are not revolving around the nucleus in orbits. Instead of being located in orbits, the electrons are located in what are known as orbitals, right? So the orbital, by definition, is a region in space around the nucleus where the probability of finding an electron is very high. And what you'll find is that based on the energy levels as predicted by the Bohr model, we have basically the same energy levels according to the Schrodinger approach, according to the results of the Schrodinger approach. So the wave mechanical model predicts discrete principal energy levels within the atom, and these energy levels basically the same as the orbits in the Bohr model. So the Bohr model does help, but as we said before, there are some limitations, and this is where the Schrodinger approach comes in to bring more light to our understanding of how the electrons are arranged in the atom. So this is basically the Bohr model in terms of the energies of the different orbits, right? Now, according to the wave mechanical model, we don't call them orbits. We call these energy levels, basically. So we have the n equal 1 energy level, which is the energy level representing the electrons which are on average closest to the nucleus. Then we have the n equal 2, we have the n equal 3, we have the n equal 4, and so on and so forth, up to infinity. All right? Each energy level is assigned what is known as a principal quantum number, which must be an integer starting from 1, n. All right? And as I said, increases, the electron energy increases. Okay, so this is basically, well, let me just say this. There's a lot involved in terms of going from the wave mechanical model to what I'm showing you here. As I said before, thankfully for you guys, you don't need to know all the details about the calculations involved. So what I'm showing you here is basically the result of the Schrodinger calculation. So based on the Schrodinger calculation, for the n equal level, there's what is known as 1s sublevel, right? So basically, this sublevel is present within the n equal 1 energy level. Within the n equal 2 energy level, there are two sublevels, 2p and 2s. Within the n equal 3 energy level, there are three sublevels, 3s, 3p, 3d. And within the n equal 4 energy level, you have four sublevels, 4s, 4p, 4d, and 4f. All right? So basically, each energy level has sublevels, and the number of sublevels is dependent on the particular energy level. Okay. Now, within each sublevel, you have electrons that are found in orbitals. Now, remember what we said. Orbitals are basically regions in space where the probability of finding an electron is very high, all right? So the s orbitals, like the 1s orbitals, the 2s orbitals, those are the orbitals that you'll find in those sublevels. They all have this shape, a spherical shape, right? So this is basically what the shape of the s orbital is, what it looks like, all right? And as we said before, that orbital is a region, a spherical surface, which encloses a space where there's a 90% probability of finding the electron within that space, all right? So that's the s orbital. Now, this is true. This statement right here is true for any orbital, not just an s orbital. An atomic orbital can hold a maximum of 2 electrons, right? So each orbital, including an s orbital, can have a maximum of 2 electrons. Now, if those 2 electrons are occupying the same orbital, they must be spinning in opposite directions. And we use these arrows to indicate the direction of spin. So one arrow pointing up representing the electron spinning in one direction, an arrow pointing down represent the electron spinning in the opposite direction, right? So if you have 2 electrons occupying the same atomic orbital, they must have opposite spins, right? And this is largely as a result of a law known as the Pauli exclusion principle. All right. I won't go into what the principle actually says, but one consequence of this principle is what I just stated. If you have 2 electrons occupying the same orbital, then those 2 electrons must be spinning in opposite directions. All right. So that is what is being shown here. That's 1 electron. This arrow here represents 1 electron spinning in one direction, and the other arrow is showing the other electron spinning in the opposite direction. Okay. For the p sublevel, what you'll find is that within any p sublevel, there are 3 what we call p orbitals. And the shape of these p orbitals are what you see here. The p orbitals are oftentimes referred to as dumbbell shaped. And the way they are oriented in space is as you see here. If you think about the 3-dimensional Cartesian system, you'll have one p orbital aligned along the x-axis. We call that the px orbital. You have another p orbital aligned along the y-axis. We call that the py orbital. and then the third p orbital is aligned along the z-axis. We call that the pz orbitals, right? So this is what they look like separately, all right? So as stated here, each p orbital has two lobes, and there's a point in the middle which is called the nodal point, all right, where the probability of finding the electron is 0. And as I stated before, like any other orbital, the p orbital, each p orbital can have a maximum of 2 electrons, no more, all right? So therefore, within the p sublevel, within any p sublevel, the maximum number of electrons that can be accommodated by that sublevel will be 6, all right? And this is what the p orbitals look like together, all right? So that's how they're arranged. And as stated here, they share a common center right here. And the p orbitals, of course, are pointing in different directions. So they basically have mutual right angles to each other. So that's a px, that's a py, and that's the pz orbital, all right? When it gets to the d sublevel, they're made up of 5 orbitals, and this is what they look like. And if I were you, I wouldn't even be concerned about the shapes of these. I'm just showing you so that you know that they exist. So these are the 5 d orbitals, all right? And each d orbital can have a maximum of 2 electrons. So therefore, at the d sublevel, there's a total of 10 electrons, all right? Okay, so to summarize, for the 1s sublevel, we have an s orbital. For the 2s sublevel, we have an s orbital. So s orbitals, they appear singly in any particular sublevel. But when you get to the 2p sublevel, you have 3 p orbitals, all right? And then when you get to the third shell, where you get to the 3s sublevel, you have a 3s orbital. When you get to the 3p sublevel, you have 3p orbitals, 3p orbitals. When you get to the 3d sublevel, you have 5 3d orbitals, all right? And so on and so forth. For the 4s sublevel, you have an s orbital. For the 4p sublevel, you have 3 4p orbitals. For the 4d sublevel, you have 5 3d or 4d orbitals. And then at the 4f sublevel, which I won't even show you, you're going to have 7 f orbitals, all right? So this is basically a summary of the different subshells within the different energy levels, right? So for n equal 2, you have 2s and 3 2p's. For n equals 3, you have 3s, 3p's, 3 of them, and 5 3d orbitals, and so on and so forth. For our purposes, we'll stop at the n equal 4 energy level, and this would be the orbital distribution for that energy level, all right? You have higher energy levels, but for our purposes, we won't go beyond the n equal 4 energy level. Okay, we're going to stop here. So the next video will be dealing with the hydrogen atom and some other things. Until next time.